Good morning.
Morning. Good morning, everyone. Okay.
Good morning.
We're preparing for the weekend, right?
Definitely.
Okay. So there will not be lab class today. We'll be using the lab time for the revision, just like we did on Wednesday. And for next week, there will be lab. So we'll use the class time on Wednesday for the tests, and then we'll come to school in person as usual for our lab experiment. I'll also upload the lab material for next week over the weekend, if not before the end of today, okay? And the instructions of what to do. So it means if there's lab by next week, we are expected to turn in our lab report as we are coming into the lab, okay? So you come with a copy. So immediately you come in, please turn it in, because the person will come and pick it up for marking as soon as we start our class, okay? All right, so let's just begin today's interaction, which is the third part of our chapter 5 class. So today we'll be looking at the whole chapter is talking about applying Newton's laws in solving physical problems. So we've looked at how we applied the first and second law, and we kept looking at several applications of how we applied the Newton's laws when we saw some examples. Okay, if you can keep your questions in the chat before the end or at the end of the class, I'll reply. Okay, so we're looking at the Newton third law. We know that in our last class, when we first of all looked at the Newton third law, we established that it is that law that talks about interacting objects And also we emphasize that it is actually the law that brings to bear the action and reaction pair of forces, okay? So which we see in interacting objects. As you can see in the image here, the object A and B having contact with each other. The effect, whatever force you apply on A have an influence or affects B, okay? And when these two objects are interacting, they tend to move with the same acceleration. All right, so these are just the emphasis of Newton's third law, and this will be what will guide us to solving physical problems as it applies to interacting objects. So let's do a quick reminder of what we said about Newton's third law. We established two basic points when we looked at Newton's third law. We established that every force occurs as member of action and reaction pair of forces. Okay, and we also emphasize that the two members of the pair of forces always act. One moment, my pen is not activated. Okay, always act at different, always act on different objects. So the object B is acting on a different object, object A, while object A is acting on a different object, object B. Okay, so we also emphasize the second point that the two members of an action-reaction pair point in opposite direction. Okay, so and also the direction is opposite, but the magnitude are equal. So the direction of the force from A goes this way, while that of B will go this way. So they point in opposite direction. These are the facts that will help us in this section that we want to look at. We'll see how we apply the second and the third law to analyzing objects interacting with another object. Okay. So let's quickly look at the tactics like we used to, that we'll be using to solve problems of objects interacting with another object. If we have two objects in contact and their motions linked, we have to follow these 6 basic steps to analyzing how we arrive at the solution required of us. Okay, so the first thing we'll do is to draw each object separately. Yes, the description of the interaction will show clearly that these two objects are interacting with one another or in contact, physical contact. But to analyze or solve the problems that we want to look at, we'll first of all have to draw each object as though they are separate from one another. So this is to help us separate and identify the forces from the diagram we will make. So the next after separating the object will be to do a free body diagram. And you know what the free body diagram helps us to do? Identify the forces and also emphasize the direction of the forces. So once we notice that, as immediately we finish drawing our free body diagram, we are able to, from the free body diagram, tell the component of force and their magnitude, pointing out also the direction. All right, we always follow this Newton's second law that says F equal to ma. Okay, we use that to write the component of the forces. And from the free body diagram, we'll be able to show the magnitude and their signs, which is their direction. So the first 3 things we do is separate the object, draw the free body diagram, write out the components, the X and Y component of that force, which is the summation of the force, will be equal to ma. So immediately we are done with those first 3 steps. The next thing we do is to identify the action-reaction pair of interest. Okay, so if object A acts on object B with the force that will tag FA on B, then we identify the force, the reaction pair of that force A on B, which will be force B on A. So we have to look at the description of the problem given to us, bring out the action reaction pair of interest, then we'll proceed to applying the component force equation to arrive at the solution we hope to look into. Then we use the Newton third law always come into play from the beginning of our analysis. And what is the Newton third law going to emphasize? You know, for every action, there's equal and opposite reaction. It tells you that we can actually equate the magnitude of the two forces because they are equal. The force A acting on B will be equal to the force B acting on A. Because an action will give you a reaction pair. And you know that this reaction is instantaneous. It's not like after, as one is happening, the other one is simultaneously happening alongside. Okay. So we'll also look at the very last one, which is the fact that the objects that are in contact, this is simplified kinematics. It means we can easily tell their direction, even if we don't, because when we want to emphasize the forces, we have to like separate the objects. But from the description, it's a simple kinematics, and we know that object in contact will have the same acceleration. So we will have F equal to MA, and the acceleration will be the same. All right. So we have also emphasized that the force action force will be equal to reaction force, and they will have the same acceleration. Those 2 points we should always keep at our fingertips. So for an object in contact, say a force A acting on B as seen in the block diagram here, A acting on B, that's what we use to explain the object in contact. So force B acting, force B on A acting on block A, that is the force of the block B has the highest mass, yes, but we see the force B acting on A having the same magnitude. So we have emphasized this in the 30s, but we're just bringing it out as it relates to objects in contact, which is interacting object that we're looking at in general. We have also established that they will have the same acceleration. So this slide is like a repetition of what we saw in the 30s, okay? So, and like I said, don't be bored of seeing repetition in some of our lectures because it is the law of deep and lasting impression. We want this to stay in your mind. We want you to always think of Newton's third law and remember these things, that the magnitude of the force acting on each other is the same, the acceleration is the same as well. And these are the things we use to solve problems. So for solving problems of objects, interacting objects, we have to solve the two problems in parallel. We have to consider the two objects and also use the basic information to solve them in parallel. So let's quickly look at the first example. In figure 1C, that's what I named it. It might not be the same label in our test, but it's also an example in our textbook. So figure 1C shows a 5 kg block A being pushed with a 3 Newton force. In front of this block is a 10 kg block B. The two blocks move together. What force does the block A exert on block B? The two balls are moving together, so we already know the opposing forces, the magnitude will be the same, the acceleration will be the same. So this is the pictorial representation of the description of the first mass A, which is 5 kg, and the second mass, which is 10 kg B, and they are both moving on a frictionless surface. Okay, the question said they both moved together. So using our steps in the 30s, we said first we'll have to separate or visualize the objects separately. Look at object A separately and look at object B separately. So we see that the force of B is backward on A. B will react to the action that A is bringing. Okay, so we see the direction of the force of B and see the direction of the force of A. Okay, so the force of B is backward. We see the hand that is pushing. We see a long range force, which is a weight pulling on the object, and we see the object resting on the surface, which will bring in the normal force. Now for B, we have the force of A acting on it on this side. Okay, this is where the force of B will act on this. That's the surface of contact. And then we'll have the weight and also the normal force. So the next will be to do the free body diagram of this particular force. Okay, so let's look at the free body diagram. The force on the hand pushing at the object A is acting in the same direction as the force of A on B. You can see the force on the earth from the hand acting in the same direction because it is that force that actually set the two objects in motion. We see the direction of the force of weight always pointing downwards. Okay, so we see the force from B acting on A going in the opposite direction as the force of A on B, which established all we have been saying about the action having equal and opposite reaction. So we see the normal force. We said the normal force is always acting perpendicular to the surface of contact. The object is resting on the surface, and the normal force is acting perpendicular to that surface. So we see it point upward, opposite to the force of weight that is on that object. So we'll see the free body diagram for object A, and we see the free body diagram for object B. Okay, so from the question that was given to us, they gave us the mass of A, and they gave us the mass of B, and they gave us the force from the hand, and they asked us to look for the force of A on B. All right, so the force of A on B, the force that is pushing forward, that is actually coming from the force of the hand, setting the object A to influence the object B, and they both move together. Okay, so we said that the next step will be to identify our action-reaction pair of forces. So we'll see that this is our action-reaction pair of forces, that is force of A on B and force of B on A. Okay, because it is this that will help us know where to focus on when we're analyzing or solving our question that says we should look for the force of A on B. So having done the free body diagram, the next thing we did was to write out the components of that force. Okay, we see that when we read the question, we'll be able to tell that the action is only on the x-axis. The object is moving on the s-plane. Yes, we'll have the force of the normal force and the force of weight acting on it, but actually the action of what that object is and the question or area of interest in the question is only on the s-plane. Okay, so that is why we just bring out the equation, writing out only the equation of the s-plane in this case. So we write the Newton second law equation for the component of each block. All right. So let's look at the Newton second law S component for the block A, which is the summation of forces acting on that object A equal to MA, mass of A and the acceleration. The two of them have the same acceleration as we stated in the basic fact about interacting objects. So we'll have the force of the hand plus the force of B on A. These are the two forces in the X direction of A. While on the B side, we have only one force in that X direction. So we'll bring out the S component plus this equal to this. Remember that when we are expressing the equation, we're using summation, but when we now want to express in terms of magnitude of that component, that is when we factor the direction. So that is when we can say minus, plus, and other. But when we are writing out the equation of the components, everything is plus, because we are emphasizing that it's the summation of the force. Whether the force is pointing to the positive or negative direction, it is a summation, okay? So we proceed to putting the magnitude or expressing the same equation in its magnitude form. We see the force of the hand pointing to the positive or right direction, and we see the force of coming from B on A pointing to the left, which gave us the negative sign that I'll put here. So we'll have F H, sorry. So we'll have F H minus FB on A to give us MA, mass of the first object times the acceleration of the first object. So for B, the object B, we see that we only have one force on the S component. So the summation of the forces is simply the force of A on B. And that is the question they asked, the particular force they asked us to find with the information given. So with this information that the acceleration of both objects will be the same, we will now take the equation B, because we'll have several unknowns. So we'll try to go from what we know to what we don't know by simplifying and substituting, as we did in the equation we derived the other time in our assignment 2. We use the same basic mathematical rules. So in this case, since AS is the same for both, we'll make AS here the subject of formula. So we'll have AS will be equal to the force of A on B divided by the coefficient of object I'm making subject of formula. All right. So that's what we have here. So we can substitute this into the first equation, which is the equation for the object A. All right, because the acceleration is the same. So where we see acceleration in the A, we can put this into the position. So we have seen that the first equation is the sum of, this is the one we are using to solve the problem, FA minus FB, then A. So we are substituting for this A. So if we put that FA, FH minus FA on B, we know where this is coming from. Okay. From this. All right. MA, our A is F A on B over MB. MA is already existing there. So we just added this to give us MA over MB. This is the force we are asked to look for. Okay. So from this equation, we can then solve for FA over B. Now we make this the subject of formula in this equation. How did we arrive at this? Let this one move to this side, or such that the sign of the minus sign becomes plus. So you have something like this, MA over MB FA on B. It has moved to the other side, A on B. So we see A on B here. So we can actually write this as FA on B 1 plus MA over MB. So if you open the bracket, you also get the same thing here. So we did this because we want to make this the subject of formula. All right. So to make this the subject of formula here, after separating this, we have to divide both sides by this coefficient. So that is how we got this equation here. Is it clear or kind of confusing? I want a response from the class, please.
It's a little confusing, but I think I get it.
Okay. So when you try to write it out on paper, because when I try to use this, it usually appears if the ink is just not writing clearly. Or maybe because I'm not resting in the right way I should. Okay. So, but that.
One question, the 1, what does that from? I just want to double check.
Okay. So what we did from this step was to move this, cross the sign of equality to this side. So when we do that, we'll have an expression that appears like this. Okay. MA over MB FA on B. The one we moved becomes plus because it has crossed the sign of equality. It becomes FA on B. Now we see the like term in these two equations, so we can bring it out. If we bring out the like term, A on B, this is 1 from here, plus.
Okay.
Okay, so that is where the 1 came from. So when you open it up, it will give you the same thing here. So immediately we'll have this kind of expression. It's going to give us something like FH equal to this. So make this the subject of formula in this equation. Divide both sides by, or multiply both sides by this. Yeah, divide both sides by this. Sorry, not multiply. I was reading this apart. So if you divide both, multiply both sides by the coefficient of yes, coefficient of the object you're making the subject of formula. It's not multiply, but I'm just using the word interchangeably because some of us, instead of saying divide both sides by, we used to say multiply or divide, sorry. But in this case, we're dividing both sides by the coefficient of the object we're making the subject of formula, which will give us FA. That is the expression we have here. Okay. All right, so I haven't arrived at the last expression for F first acting on A of force of A acting on B, which is the force we're asked to look for. We just substituted the parameters given. Okay, your hand is raised, Chamaka. Can you come on the mic?
Yeah, I want to ask why we equated the two equations together. The FH minus F A on B is equals to MA over MB. This equation that you circled.
This
Why
one?
Did you? Yes, the one. Yes, this. Yes, yes.
Okay, if we follow from the start of the solution, we first of all express for A, and then we now, because we said in our tactics that we'll be solving this equation as parallel to each other because they are interacting forces. Okay, so the information from equation component of B, the information we got here, helped us to solve for A. So what we did was to substitute for A into this equation. Do you agree to this point?
Yes.
Okay. So what we did from here was not equating the two. We substituted for A. Okay. So anywhere we see A, we put in the value FA over MB. So we did not just equate the two, A and B, or say A equal to B. Yes, we know that the force acting will be equal in magnitude to the force reacting, okay? But we brought out the expression, made A the subject of formula from the fact that both of them will move at the same acceleration. We now substituted into this equation. That is how we got this. So we did not just equate the two. And we said from equation 2, we obtained A and substituted into the first equation. So it's not equating equation 1 and 2. Is it clear?
Yes. Yes.
Okay.
Thank you.
You're welcome. So we now put in our values. The first from the hand is given. Every other parameter is given, and we obtain the force of A acting on B to be 2 Newton. So let's look at the last part of the discussion for today, which is the rope and pulley. Now we have seen rope. We have seen the kind of force that acts on the rope as what? The tension force. And we emphasize that the tension force will always be in the direction of the rope. Okay? So if the rope is pulling to the right or left, that is the direction of the tension force. But in this case, we bring in an additional form that we call pulley. As we can see in section B, we have the same rope, one rope, but it's going to cross a frictionless, massless, frictionless pulley. All right, and it's changing direction once it does that. So we're not really emphasizing the part of the rope because we want to believe that we have full understanding of how tension force acts on the rope. But the only additional information we have now is that of a pulley. What happens if this rope is bent over a frictionless, massless object, which we call pulley, and it changes direction? What will happen to the tension on that rope? So we are emphasizing that the tension on that rope or string is the same. So the tension on this side is going to be the same as the tension on this side. It is still the same rope, as long as it is being passed through a massless, frictionless pulley. It's not going to have influence on the tension force. The only thing is the direction. Okay, it bends to this side, but the tension force is going to be the same. Now, this is the understanding that will guide us throughout the approach to solving problems relating to the tension force on a pulley system. So a pulley system is moving a rope around a massless rolling surface, okay? A massless, frictionless rolling surface. Now, another thing we want to introduce is what we now call the massless spring approximation. And the reason for this is that we want to be able to apply the Newton's second law to solving problems as it relates to tension on ropes and pulley. Okay, so we'll see the first example here, which is the basic one we know. If a hand is pulling on a rope, we can bring out an interacting object force from this diagram. We'll see the boss and the rope interacting. Okay, so we'll see that there will be a force from the boss to the rope, and there will be a force from the rope to the boss. But in describing this kind of interaction, we see that The bus is resting on a frictionless surface, but the rope is tied to that bus. So on the rope side, we cannot really bring out the force that is the not normal force making that object to rest on the surface, and the weight. So because it's not really something we can easily bring out, because we have to describe the normal force as resting on the surface. And they are also interacting forces. We now introduce what we call the massless string approximation. And what does the massless string approximation say? It's saying that the mass of a rope is 0. That means it's negligible. We can actually neglect that. And if that is the case, it means it will help redefine the Newton's second law on that rope. So if we see this kind of interaction and we want to bring out the Newton's second law expression of that rope, we see that rope emphasize the forces on the x direction. So the summation of the forces on the rope will be the force from the hand and the force of the rope, of the bus on the rope, which is opposing the force from the pull. Okay, the tension force is the force from the pull. So we'll have that the force from the hand minus the tension force equates from MA, mass of the rope, and it becomes 0 because the mass of the rope is already 0 from the massless string approximation. Okay, I think we understand it better when we look at an example. So quickly, let's look at the tactics we will use to solve problems as it relates to rope and pulley. First, we'll factor something that we said, the Newton's second law in this case will be 0 because there's a massless approximation which from the rope, and we have said it is 0. So that influences the whole expression, okay? So we are going to assume that every problem we'll be solving will be an ideal case of a pulley. The rope is going to go through a frictionless surface, so we'll not have interfering force. All right, so what are the tactics we're going to use to solve this kind of problem? We'll have 3 basic steps for massless rope on string and massless frictionless pulley. That means we can actually ignore the mass of both object, the rope and the pulley. Okay, so if a force pulls on one end of the rope, we're establishing some facts in this statics. The tension on the rope is equal to the magnitude of the force pulling it. It's also emphasizing the Newton's third law, which is the action will be equal to the reaction in magnitude. Okay, so if let's say you are pulling, because there's a first example we ought to look at, but it's a conceptual example, 2 persons pulling on a rope from 2 ends with the same force. Okay, the tension on that rope will have the same magnitude. We have another case where you tie a rope on the wall and you're pulling at a particular or known force. The tension of the wall or the pull back from the wall on that rope will be equal, okay, in magnitude. So if 2 objects are connected by a rope, the tension will be the same at both ends. Okay, we'll see that also in the example we'll look at. The third point we'll keep in mind is if the rope passes over a pulley, the tension on the rope is unaffected. As we have seen in this case, the rope is passing over a pulley, the tension is the same for both sides. Okay, so let's see example, which is the last example we see today. The question actually is on these 2 parts. So this is just a description of what we see mostly in an everyday life. For a serious fracture on the leg, we use what we call traction to treat fractures or bone fractures, okay? So, and we apply the law of physics in this treatment. That is, you should appreciate how physics actually help us to analyze the physical event around us. Look at how physics is being applied here. Using simple law of the third law of Newton and applying it over the rope and pulley system. So for serious fracture on the leg may need to have a stretching force applied to it to keep the contracting leg muscle from forcing the broken bone to heal wrongly. Let me use that word. That is to come together too hardly. Because when that force is not controlled, we see that the healing process after the person is healed, the person kind of gets deformed in a way that physiology-wise, the shape of the leg might change, the hand, or the area that was broken. So we'll see that it is actually improper treatment that makes us see such kind of deformation. But if we have a proper alignment of our forces, it will help control the contraction of the leg muscle to bring about proper healing. So this is often done using the process called traction. And traction is simply an arrangement of rope, weights, and pulleys. Okay, so we picked this example because it is one example that will show us the effect of all the forces we have been looking at and how we apply the laws to solving it. Okay, so traction, as we will see in the next figure, is the arrangement of rope, weights, and pulleys. So the rope must take the same angle on both sides of the pulley. Why is the emphasis on the angle? Because it is that angle that will help you properly set or define the kind of force you apply, given the principles as stated in the tactics. Okay, so that the net force on the pulley will be on the horizontal opposite to the position of the leg. Okay, so but you can make adjustments on that angle to control the amount of traction, which is the force that can be applied in that system. So a doctor, after setting up this arrangement of rope, weight, and pulleys, instructed that they apply a 50 Newton of traction, that is force of 50 Newton, on a patient using 4.2 kg hanging mass. What would be the proper angle that we should keep between this pulley system, both pulleys? So let's quickly see the description of what we just read now. This is the fractured leg. So the fractured leg has a set of traction, which is pulley, rope, and mass, which is weight. So it was set such that the simple arrangement of rope on the leg, the control of forces using the pulley, such that this position of these two pulleys and the angle will give the net force to pull, as the force of the pull on the leg, to the right, which is going to be opposite to the pull back from the leg. So let's present a free body diagram of this analysis. So the free body diagram clearly states the direction of the force of leg on pulley is going to be pulling back, while the net force here is pulling forward, pulley on leg, opposing. So we see that it is actually this and this that forms a kind of action-reaction pair also in this scenario. So the force on the leg is reaction to the force on the pulley. So this reacts to this, and that's why they're opposite in direction and they are acting on different objects. Okay, so we'll have the tension force here, and we'll have another tension force here, and they both have the same angle. The net force will pull in the direction of the force we want to achieve. Now the question says, what will be the proper angle to achieve the kind of 50 Newton force that we want? So we start applying the 30s we have seen earlier. We emphasize that the tension, they are equal in magnitude. The tension on the pulley, that is the tension, we see T tension here and the tension here. They are equal in magnitude, all right? Now, we emphasize that this net force is 0 because the object is at rest, it's not moving, following Newton's second law, as seen earlier. So the second point we would like to keep to guide our approach as well is that the tension is the same throughout the rope. Why? Because the rope is passing through massless, frictionless pulley, okay? And then if having the information, since we have the information that the mass hanging on the rope is 4.2 kg, we can actually look for the force T, the tension force, using this equation, okay? So T equal to mg, we know what G is. If we use G to be 9.8 or 10 in some cases, which will specify, take G to be 9.8 or 10. So if we use G as 9.8, we'll see that the force of tension is 41.2 Newton. So we know the force of tension, we know the force applied. We want to work on the angle. What will be the proper angle? So keep the diagram, the free body diagram in mind. So the pulley is at equilibrium. How did we know that the object is not moving? Okay, so we have seen our static and dynamic equilibrium. So this must satisfy the Newton's second law that says that the acceleration is going to be 0. So the sum of the forces, in expressing it in form of Newton's second law, on the S-plane is going to sum up to 0. Okay, so we'll have the two forces from the tension and the leg on the pulley giving us 0. The leg on the pulley giving us 0. Okay, the force of the pulley on the leg is actually, which is this one, pulley on the leg, is actually represented here. It is actually the net force or resultant force on these two tension. Okay, so we'll have the action reaction pair in this equation, obeying the Newton's second law, and the static equilibrium as 0. So those two information will help us in proceeding further. So the tension forces, we have emphasized that they will have the same magnitude. So the magnitude on TA is T1 is the same as the magnitude of TB, and both are at the same angle from the horizontal line, from the S line. Okay, so the angle on both, as seen in this diagram, is also the same. All right. So the S component of the leg force is negative because it's pointing to the left. Using that from our Newton's second law, some of these forces, this one is going to the left and this one is going to the right. Action pair and the acceleration is equal to 0. Now, how did we get this 2T? We know the resolution of force, okay, for this S component is going to be what? Let's make a projection, for example. Sorry, something like this. So we're having opposite over adjacent. So that is why we have T will be cos theta, and T1 will also be cos theta because we're looking for the S component as defined from this angle, okay? So if we say these two, they are the same magnitude, T1 plus T2 eventually give us 2 the T tension is the same in magnitude and the angle is the same. So that's how we got this T2. So it's actually the same expression as this. T1 and T2, they are the same in value, magnitude. So we can actually add both to give us this. Minus the leg on pulley to be equal to 0. So move this one to the side. So you will have T2 cos theta will be equal to F of the leg on pulley. All right. The question asks us to look for at what angle. So we're going to divide both sides with this. So we'll have cos theta being equal to F of the leg on pulley, force on the leg on pulley over 2t, which is what we have here. Okay. So we'll substitute the information we have. This is given 2t. We got our t to be tension is equal to mg, remember, 41.2 Newton. No, yeah, 41.2 Newton. 41.2 plus 41.2 gave us 82.4. So we'll have cos theta equal to this. Take the cos inverse of this value. We'll have 53 degrees. So we'll see that at 53 degrees, we can actually vary our setup of traction from 53 or angle 45. If you look at this diagram, this is horizontal, vertical. You see that this is an angle 90. They can actually, we can vary this traction to move between angle 90, okay, to achieve the certain weight. But to achieve this weight, we vary at this angle. But to have the maximum force, we can actually vary this 45 on this side, 45 on this side to give us a total of 90-degree angle difference, 45, 45. But in this case, we had 53 degrees as the best angle to achieve or obtain the 15 Newton friction. Okay, so the remaining part is just to check understanding. I want to quickly say that I already have some of the lectures. It's coming on Moodle. I'm not able to just upload everything at once because of the kind of system I'm using. Everything cannot go at once, so I have to allow some to go. But by the end of today, I should be able to put up more. I don't know if some of us have seen the lectures. My concern is I want a case where once I put it up, you receive a notification and then you go and watch it. I won't have to post the link on Moodle because that means I'll be posting like 3 links every week. I don't know the best way we can do that so that you can receive notification. If it's directly on Moodle, immediately I post it to send a mail to you. But because the volume is, the size of the file is more than what I can put on Moodle, that is why we're using YouTube, okay? How many of us have seen the lecture videos? And if you have questions, please, about today's class, please ask, okay?
Could you upload the link, or could you send me the link for the YouTube lectures?
The link for?
YouTube lectures, the YouTube, you said you're uploading it on YouTube?
Yes, I put the link on Moodle.
Okay.
I've put 3 of the links. I have more than 3 lectures uploaded, but I just put 3, the link on Moodle. I'm just thinking of a way such that once I upload, you just get a notification. Is there a way to do that? Apart from asking you to subscribe on the I know that if you do subscribe on the YouTube, immediately I upload a video, you will see it. But is there another way to get a notification apart from that? I don't know.
You could ask the IT services at Brandon U. They would have a good answer. The
Okay.
YouTube notifications and email, just off the top of my head.
Okay, so that once I upload, you receive an email notification. Okay, I'll see how.
Which chapters are covered in the test?
We're
on
doing the
that
test.
side?
We're doing the test on what you have handled so far, chapter 1 to 5. Okay. So you have the weekend to study. You also have the Thanksgiving Day. There will not be classes. Okay. Which is on Monday. And then we'll come on Wednesday. That means we'll be meeting. The first contact will be Wednesday, which will be our test, then followed by our lab class. Okay.
Question about the lab. Because the one we were working on is like, you said it was like a 2-week long lab or something. So do we have to have it finished for
Yes,
this lab class?
yes. You finish up your report. If you have any questions, send me a mail, because the second part should have been, the reason why the lab class is usually two parts is the first lab, you use it to do data collection. That is, you go to the field, which takes the whole day. Okay. So we didn't do that. We just supply the data to you and then ask you to do the computation. Okay, I'll be creating. I didn't get you. I'll be creating a link.
Excuse me, before you continue, you
Okay.
mentioned we're having the midterm next week, Wednesday,
Yes, on the
from
13th.
10. Yeah, it's normal class time. Does it run into? How long is the time limit you give?
It's an average of 50 limit time, which is the
Okay.
time for the class. But
Okay.
I don't know if some of us can come or join early,
Oh, okay.
so that if you have a computer or a printer in your room or where you'll be using, you want to quickly print out the question, but you will not be allowed to leave the scene to go elsewhere to print out the question.
Okay.
So the question will be projected. If you want to print it out, you can quickly do that under the view of the person watching.
Oh, okay.
Okay. So that will mean that if you have the time to join 10 minutes earlier, please do, so that we can use the 1 hour, complete 1 hour. If you join early, you'll be able to finish and submit early. We'll have the multiple choice the same way you had on the lab quiz. You have to tick those ones on the system. Then you write out the theory parts will be written. You get a device that can easily snap, then you submit on the module link.
And you said there's a lab exam in the afternoon, I think?
Not exam, yeah,
Well,
normal
quiz
lab
or something?
class.
Oh,
No,
like
no,
normal
no.
lab class. Oh, okay,
No.
okay.
I'm just saying the lab quiz, you have seen the lab quiz. I'm saying the multi-choice question is going to come in that format.
Oh, okay, okay.
Okay.
I see what you mean.
All right.
Okay, well, thank you then.
Yeah, so I'm going to be putting up the formula sheet on Moodle. So if you have a correction or contribution to make a formula you want me to include, I'll add that. We'll make the correct copy available if we're not able to quickly correct and upload the updated copy. And then the instruction on what is expected will be given as well. But note that there will not be washroom break. Okay, so just prepare yourself such that you don't have to need a washroom break, please.
And you said it's open, it's closed book?
It's closed book, yes.
Okay. But with our cameras on facing, you want to see our face and the papers, I think you said the last time?
Yes, your face, your paper, once your hands on the desk, you're not going anywhere else. And your volume should not be on mute. Okay, and I said that if you want me to check if you're certain it's okay, you can give me a message that please can you check to see, then I'll just connect on Zoom to see the environment where you are. Okay, I wanted us to use Monday to do a kind of mini rehearsal of what is expected, but we have a holiday, so we'll do that on.
Well, well, I'll be down for that if you want to give like a live review on a Monday on Zoom at regular class time. That would be perfect for me.
Okay, So if you can come on regular class time on Monday so that we just check the settings, see how we'll be able to do that. Let me
And sorry, I
see.
didn't hear. Is it multiple choice and it's a mix of multiple choice online as well as submitting a paper that you upload to Moodle? Is that correct?
Yes, very correct.